the investigation of near-wall processes in an optically accessible SI engine using wall-resolved large eddy simulation. Since that's quite a lofty long title, I'll motivate this in a second. I want to say, if I say we, I mean my former colleague Andrea Patti, who I'm glad was able to join us, who's now with KTM, but we conducted this research when he was still with us at STFS. So this is who I mean by we, and I'm talking about we. So yeah, what did we want to do? So you can see a video of a multi-cycle LES simulation of the Darmstadt engine. The Darmstadt engine is an optically accessible engine that our partner institute RSM investigates quite heavily. Tomorrow there will be a talk by Mr. Böhm on this particular engine and the approaches they take. So I won't spend too much time on the engine. It's an SI engine, 86 millimeter stroke, 86 millimeter circumference, and 700 cc's, 800 cc's, sorry. And this particular operating point that I'm showing you here is at 800 RPM, motored, no combustion. What we wanted to look at is, obviously this is a tumble engine, and what we wanted to investigate is the boundary layer on the piston top. We chose this region because, as you can see, it's really resembles at first sight maybe a flow over flat plate. So you can see you have a tumble here and a flat piston in this engine, and so the assumption is quite natural to say, okay, this looks sort of like a flow over a flat plate. The other reason we chose this engine and this configuration or this location to look at is that we have experimental data we can compare to from the RSM. So our objective was, okay, we compare to the experiment and we see along this boundary layer on the piston top, do we follow what you can see here? I hope you all know this or remember this. This is the sort of very characteristic log law curve you get with in a turbulent boundary layer with the viscous sublayer here, the buffer layer, and most important, and what we sort of always look for if we can find it in the engine, the logarithmic region. And this has been investigated experimentally and also numerically. But of course, the engine is very complex. You have different operating points. You have different engines. So this is what we want to do, and this is what we want to look at. Just some small pointers on the setup. Of course, we use OpenFOAM and TF Motion. TF Motion has been called the cousin of libice, and so it's our modification of libice. In the present study, I have 33 LES cycles that we can then ensemble average to predict the data. The operating point, like I said, is at 800 RPM, 0.95 bar intake pressure, so quite slow RPM, but high load. The LES model, so LES simulation, is the static sigma model. The cell layers you see here, and that were also used in the gas exchange phase, but not cell layers, cell size in the gas exchange phase, and in this larger region, larger insulinder region is at 0.5 millimeters. Of course, that's not enough for wall-resolved mesh. Oh, okay. As previously seen, we also use, sadly don't have a fancy video of it, we use layer addition and removal to capture the piston motion upwards. But we have this very highly resolved piston top mesh that's connected to this core mesh with an AMI interface. And this is how we got down to a resolution of below π+1. So we can really call this a simulation at the piston top. Obviously not in the. And we also tried to make this mesh as close as possible to an aspect ratio of 1. Of course, we had to use some aspect ratio growth, but I think this is, for all intents and purposes, a really, really high resolution that we push for. Okay, so I start off with the sort of validation with the experiment. First, I hope you can all see this. We will look at the piston center, and the x-axis will be the y normal direction. And we start off just by looking at the velocities. Green is the experiment, gray is the simulation. And maybe I forgot to mention this, I don't know. We looked at this in the compression phase. So here you see crank angle time 60, 45, and 30 before top dead center. And you see quite a typical velocity profile for wall bound and flow. Really steep gradients at the wall, and then a maximum velocity, and obviously because you have a tumble, velocity decreases towards the center of the piston, of the in-cylinder region. Yes, we're going up in. We also see we have a little bit of an overprediction in the LES. Generally, we see a trend that the maximum velocity sort of trends down. Notice here that the scale is a little bit different, and we capture this trend quite well in the LES. And if we now go one step further, here are these typical U plus Y plus plots. So I scale both the experiment and the simulation. I also noted the pressure gradient here. This will become a little bit important in a second. Generally, we see quite good agreement between the experiment and the simulation if we actually non-dimensionalize the data. And what we can already recognize, and quite good that we capture this, is we don't see a extended logarithmic region. So you have no region where this is really adhering to this log region. I mean, this is one already essential takeaway. And what we also see, as I noted, the pressure gradient in the piston center for 60 and 45 degrees before top dead center. At the piston center, we have a favorable pressure gradient, so you have a flow that's being accelerated, and this flips around. We get closer to compression. Now, I need to go on a little bit of a tangent with this scaling, which is, again, which is, of course, in an engine, you don't just have a velocity boundary layer, but you also have a temperature boundary. Now, when you do this non-dimensionalization, obviously you have the viscosity and the densities in these terms, and so those are temperature dependent. Now, typically in a incompressible channel flow, or DNS, where this is often where this was established, temperature is constant throughout as you go away from the wall. Engine, of course, it's not. You have a difference between the wall temperature and the bulk flow. So the question becomes, what scaling, what temperature do you use? And especially this is sort of important because in the experiment, you don't know the wall temperature, or vice versa. In the CFD, I assume the wall temperature. And it becomes quite important that you keep this scaling consistent, because if you look at this, here what I did, I just plotted this U plus Y plus scaling from the experiment using different temperatures. So the bulk temperature, the mean temperature, which is just the value in between, and the wall temperature, and you can see this U plus Y plus plot is actually quite sensitive to this. So you can imagine if you take experimental data where they make some assumptions about the wall temperature, they make some assumptions about the bulk temperature, and then they scale their data. If you were just to compare to this, like you find in the literature, then you will get discrepancies just based on very small differences in the wall temperature. So what I elected to do was I took the data from CFD, so the thermophysical data, so the temperature profile from the CFD, and I scaled the velocity data from the experiment. So that's how we got the plots you just saw. So to summarize it, basically, I always use this t-mean and apply this to the experimental data so that we have a sort of fair comparison between the experiment and the and where this also plays a role, and this is I also think very important, is if you then go and look at incompressible DNS data and you make interpretations based on this DNS data, especially pertaining to the pressure gradient, where in incompressible DNS, what you will usually find is that if you have a favorable pressure gradient, you will overshoot the log-law region. And if you have an adverse pressure gradient, you will underpredict the log-law region. So if then, of course, you think, okay, I make some assumptions about the temperature, or I select the mean temperature to do the scaling, I think you have to be very careful making interpretations whether you have a favorable or adverse pressure gradient just solely based on comparing this to incompressible DNS. So this is something you really need to be a little bit careful on. And it also means if you look at values of this reported in literature, people may use different scaling. Some use the scaling at the wall, some use bulk velocity. I've seen people assume adiabatic compression to do their scaling. So this doesn't change the fact that you don't have log-law region, but it does change the fact where you are. And if you make interpretations based on this about pressure gradient, I would advise to be cautious on this. Okay. Okay. Now I call this the tumble line. Basically, it's if you bisect the tumble plane with the piston. You can imagine you get a line, and I sample here going from the exhaust side along the piston at multiple locations, again then in one binormal direction. The color map here means that in red you're sort of on the exhaust side, and going towards gray you go towards the middle, and then blue is on the left side, the intake side. So it's basically along this tumble line, I guess. And here the color map is just a binary map based on pressure gradient. So if it's red, you have a favorable pressure gradient, meaning the flow is being accelerated by the pressure gradient, and blue is a adverse pressure gradient, so the pressure gradient in the other direction of the flow, and it slows it down. What we can see here quite clearly is as the flow attaches on the right, just the right part, you get an acceleration of the flow towards the piston center, and then this corresponds also with a reversal of the pressure gradient. You get a pressure gradient that slows down, then a pressure gradient that's a velocity that slows down, and you also see that here on the most left side you get a detachment or flow reversal. Again, what is striking here, we don't really adhere to the log-law anywhere on the on this tumble line in the piston. So in the piston center, going from intake to exhaust, and it's quite clear here also. You see here you have regions of really high adverse favorable pressure gradient. You're really below the log-law region. So this is, again, harps back to the fact to be careful when you look at these plots, because it's in the end a choice you make the scaling. So patients on. It's better to have CFD data and really measure the data rather than. What is also interesting is if you look at some of the, let's say, boundary layer statistics. So what I have here is the boundary layer thickness, displacement thickness, and momentum thickness. For all intents and purposes, they're all ways to measure the thickness of the boundary layer. Here you have the Reynolds number based on the momentum thickness, and here the shape factor, which is just the division of the displacement thickness by the momentum thickness. We can quite clearly see, and we're going along the tumble line again from the exhaust side to the intake side. What we can see in quite clearly is you catch the flow on the right side because of the tumble. And pretty much the boundary layer starts growing. There are some regions where it's decreasing a little bit, and then you have the flow detachment on the right. Notice also you have fairly low Reynolds numbers, so the flow is quite small. slow. But what we can sort of infer from this, I would say this interpretation, is if we look at literature where the shape factor, for example, is reported to be around 1.4 in a laminar turbulent transition. So in the turbulent region, usually have fairly low values of this H factor, and you can see even at the attachment point, even at really low Reynolds numbers, you already the shape factor would suggest that this is already turbulent. So you have a sort of developing turbulent, a developing boundary layer that's already turbulent, and it's maybe akin to maybe bypass transition in turbo machinery, and quite an interesting effect. If we, just as a small sort of sanity check, if we move towards the line sort of bisected by the valve plane and the piston, so a little bit out of center, basically, also going from right to left, from exhaust to intake side, you see a very similar picture. You have still acceleration. It's a little bit slower in this region. Acceleration, deceleration, and detachment, eventually going from right to left. And again, you find no log law region. It's simply not present. Of course, we have CFD data, so we can also look at this a little bit more globally. So in these plots, you're looking from top down onto the piston. I have here the wall shear stress, the displacement thickness. Here is the pressure gradient in flow direction, and this plot shows the alignment between the velocity vector and the pressure gradient. What we can see is, and this is ensemble average, so all the feed seconds, 30 feed seconds, ensemble average. We see a fairly symmetrical flow pattern on the piston top. We have large regions of favorable pressure gradient on the exhaust side and adverse pressure gradient on the intake side. And please note this is the detachment region, but this is not a reversal of the pressure gradient again, but this is when the flow direction reverses. So here you have really a reversal of the pressure gradient, here you have a reversal of the flow. What we also see is this, I call it a pressure inversion zone. It's, I would say, quite sort of crescent shaped and quite pronounced. Here you can see it a little bit better. Yeah, flow detachment is clearly visible. And also another effect that may be quite interesting and makes you go towards the realm of sort of 3D boundary layers is you can see here this sort of little shading means that you have a misalignment between the pressure gradient and the velocity vector. And what this points to is that you have some, it's called transversal forcing, pressure gradient forcing, and this can lead to boundary layers which sort of skew, and they tend to, so from what I read, they tend to skew faster in the lower part because you have lower momentum, and this is also something that's quite complex, obviously, and you, for example, do form model development, we would have to take this into account as well. Here you can see some, of course the story is always a little bit more complicated. You can see some instantaneous flow images. So these are just two single cycle realizations of the simulation. And what's quite interesting here, and let's talk about this out, okay, obviously you have strong cycle-to-cycle fluctuations, not only in the core flow, but also in the boundary layer. And so the flow features we just looked at in an ensemble average view are not quite as apparent in the single shot. So you don't, like, for example, here you see overall, yes, you have always favorable pressure gradients, but you also have very localized eddy structures that show an adverse pressure gradient and this sharp sort of inversion zone also is you can't really make it out. And same here, you see quite nicely a flow attachment here and detachment here, but it's quite hard to say where this actually happens in the instantaneous. Well, this already concludes my talk. I think we successfully showed that we can simulate these sort of very complex boundary layers using OpenFOAM and the meshing strategy we developed. We saw that, as experiments have shown, there is no region where we follow this sort of canonical flat plate theory log law region. Not only not at piston center, but we so far found no region where this happens. It seems to be turbulent. Well, some statistic points towards this. It's developing, so it's speeding up and then going down. And we see strong cycle-to-cycle variations. Where we want to take this research next is do some a priori investigations, so use the data we have to test wall functions, see what their prediction error is. Also, what's maybe also very interesting for engines is go look at the thermal boundary layer. And eventually, we want to do this all in reactive cases, so look at flame wall interaction and see how the boundary layer behaves there. And I'm open for questions.
Thank you, Max, for summarizing a couple of years' work, actually, also from Andrea, who's in the audience. Any questions or comments? I hope there's some. I have asked so many questions over the years that there's nothing left.
So first of all, we need to get done analyzing all of this. And the path forward for us that we chose is probably to go first into the reactive flows rather than increase RPM. I know there is experimental data going up, I think, to 2,500 RPM, but we're more interested first in the flame wall interaction, especially since I think this will be quite challenging. So we have to see where we spend our time. Yes, there are. Yeah. The paper I compared to, they didn't have this data available, I think, back then. And in the end, the wall temperature we assume in the LES is also we didn't have the information back then. It's I think the 16 degrees preconditioning temperature. So our temperature is in theory is a little bit low. I think the biggest effect, though, because this is motored engine, is not coming from the 30 degrees that you have an error in wall temperature, but just basically from assuming what core temperature you have or don't have. So it's the wall temperature itself, I think, is not so important, more the assumptions that you make surrounding your core temperature. Although there are also measurements for the core temperature from the engine. But in the end, I think it's okay. I chose this way to scale it and see good comparability. And I mean, the more important thing is to see, okay, do we have a log law or not? Do we don't? Pressure gradient I can measure in CFD, so I think we don't need to spend too much time worrying about the last 30 degrees in terms of.
I think the comment is very important, because I think what we need to stress is that we're all used from our fluid mechanics courses that we're all used to look at it in y plus u plus dimensions. What we really have to compare in an engine flow is the absolute numbers. Really, the velocity over real wall distance. But then we have to come back again to check our picture. Do we have adverse or favorable pressure gradients? We have to go non-dimensional at some point. But doing this properly is something to worry about, because if you do something wrong with the assumptions there, I think this is what Max showed, then you might actually end up with wrong conclusions if you just take one set of density and viscosity and some other set of density and viscosity. So I think it's really about comparing experiments and simulation in the most consistent manner. Because if you're wrong by 30 degrees in the wall temperature, it probably will not affect the simulation, because that mostly is the viscosity in the near wall boundary layer for the motor cases. But if you include this in the end, in the non-dimensionalization, that makes more of a difference. I think that's something we need to think sometimes about to make sure that we do this consistently. Please.
Yes. Yes, I think that you are comparing different things with, I mean, the standard boundary layer is measured on one dimension situation.
Mm-hmm.
It's the flow over flat plate.
Yeah.
One.
Yeah. Yeah. Yeah.
Your case, the situation is much more.
Yes.
For instance, you can have jet flow which is impinging on top. So in that situation, for example, you have, I think, no chance to match the layer outside of the sublayer. Maybe the sublayer could be considered universal in some sense, because in that region the wall dumps all features of the external flows, and you recover the standard profiles in view. Outside of the inner layer, I think you don't have chance to generalize. So also with reference to the possibility of developing some core function, I think it's quite difficult to could have a very different local flow configuration. I don't know if it's possible. I don't know. What do you think about this?
So yeah, algebraic all functions probably. I mean, yeah, you'd have to find some way to collapse this data to basically line. I think this is what this sort of community always tries to do. Yeah, I think this will probably be impossible.
This kind of things happens also in turbo machining.
Yeah.
You have a flow which is impinging on the blade. So you have kind of attachment lines, separation lines on the surface of the blade. So detachment with reattachment. So the nature of the profile is normal to the blade. It's very
chaotic.
So it's very, I think there is no chance to have a unique wall function that can match all the possibilities.
Yeah, no, I totally agree. I think it will happen, but maybe this is also the data gives us a chance to quantify how big is the error. The question is then, is this okay? If you look at core flow, does this make a difference? This is what we hope to do with this data as well.
But I think this is very important because, again, if you look at the literature, people have started using also with DNS data or other LES approaches, trying to understand the wall boundary layer structure. And I fully agree that this is way too complex to come back to something like a logarithmic boundary layer. And then, in my opinion, we had this idea of, well, if I understand the pressure gradient, then it might be closer to not the logarithmic, but above or below the line, which does also not work, because here this is a developing boundary layer. Yeah. So you wouldn't even expect that to transfer. And then we really have to go to non-equilibrium boundary wall functions that take what this notion of having production equal dissipation in the logarithmic region just does not hold.
Yeah, but I would add another degree, at least another degree, because also the direction of the flow is important.
Yes.
Only the boundary. So if you think that you can have a jet impinging on the surface just perpendicular, it's a completely different stuff.
It is.
So in this case, you can have any direction of the flow impinging. So it's very difficult. I mean, you should also consider, for example, the direction of the flow impinging.
Yes. And when you look at the RANS data, so well, it's not RANS, but if you look at the cycle average data, then it looks all very regular, right? Now think about it, Max, if you can bring up the just the snapshot of the pressure gradient again in from 1 LES. So there's basically, if you think about doing this, I mean, this is far from being a well-structured thing. So you have, as you say, a lot of local structures which you need to resolve, impingement, it's more stagnation point of flow, and you have that might be close to the wall or somewhere else. So yes, it's so complex that we probably need at the end well, you have to know where the direction of the flow is going. That's quite clear. And some advanced wall treatment, which probably needs rather than an equation than an algebraic function. I mean, there are things to do this, but yeah. But I think this shows the complexity of the flow, which is far away from being that's the boundary there. Yes. Thanks for this comment. All right, then there are no other questions or comments. Thanks, Max, again. And we have the second presentation. Here we are. So the second presentation will be combustion on. It should be on the right. So yeah, combustion optimization of a passive three-chamber Moster cycle engine and of an innovative rotary engine using open foam. So there's we're talking about advanced IC engine concept. I think that is very advanced. So floor is yours.
Thanks a lot. Thanks for the introduction and good afternoon, all of you. And so I am Gabriele Milano. I'm from More Motors SRL. That is a really small company based in near Modena. And so I'm presenting today this work that we did in a really strict collaboration with the Politecnico of Milano. And it's about combustion optimization of a passive pre-chamber that we applied on a motorcycle engine. And another work that is an innovative rotary engine that for which we optimize the combustion analysis using OpenFOAM. Sorry, it's not working. So this is briefly the topics that I'm going to present. So first of all, I have to thank a lot Professor Tommaso Lucchini that was personally involved in our work and also all of his PhD students. And I also have to thanks a lot my boss, Luca Barbarini, that allowed me and my colleagues to be here to present you the work that we did. And so first of all, a brief overview of our company. We are like 12 young development engineers that we are working in the research and development of high performance engine and also new kind of innovative fueled engine. And so we have a small technical office, but we are also working on the experimental side, so testing the engine that we then analyze through CFD software. So why we choose to have this strong collaboration with the Politecnico of Milano in order to improve also our knowledge about the OpenFOAM technology? Because briefly, since we are working in the research and development of really particular type of combustion system, we need kind of a numerical code that must be able to be customized for our aim. And also we need a software that can be used with really niche and particular kind of geometries. And so this is what we achieved using OpenFOAM. And also the fact is that the one of the most potential of the software is that it is an open source software, so can be tailored and can be customized for our needs. So the case that I'm going to present is, first of all, turbulent jet injection combustion system that we employed with a passive prechamber, and also the combustion analysis of a rotary engine that is fed by heavy fuel and is used for an unmanned drone. So these are briefly the modeling that we used. So the combustion was developed by the Weller combustion model that is also called flame era model, in which the flame development is modeled by a regress variable, and then the transition between the laminar and the turbulent behavior of the flame was modeled by the Peters correlation, and finally the laminar flame speed by the Galder one. So this is our first case, the TGI combustion. So as all of you knows, the working principle of prechamber is to have, it can be explained and divided in 4 phases. The first one is the filling process, in which the fresh mixture that is that it goes inside the cylinder by the intake stroke is pushed inside the prechamber by the motion of the piston. Then there is the first combustion that is that happens inside the prechamber, the jet ejection, and then finally the last part, that is the second combustion, or the main process that happens in the main chamber. So these are briefly the engine characteristics of this motorcycle engine, and then I really want to highlight what we found about this kind of different system of combustion. So the pros are that you normally have lower combustion duration, especially in terms of 10 to 90 duration of combustion. Then you can stabilize more the engine with respect to a conventional spark ignition engine, and you can have lower knock risk, so you can achieve higher compression ratio, and you can also go leaner with the mixer. That means having like lower fuel consumption and less pollutant emissions. But the cons of this concept is that you can have, first of all, higher heat losses due to the fact that the first combustion is happening inside a really small volume. But we discovered that the most heat transfer is on the top of the piston, actually. And then you can have possible pre-ignition of the system if you don't achieve a good cooling outside the prechamber. And you can have a possible misfire, especially in cold start, and to mount an adapter that would be your prechamber, you have to do an additional machining of your head in this case. So this is briefly what we did to mount this device, this adapter that is our passive prechamber, and we also used already present channel that we use for purging water out of the engine to cool down the prechamber. So this is what we did in-house. So we mount the engine on a test bench to test especially the performance of the engine with the prechamber installed and the emission, because the last aim of this engine was to be homologated, to be compliant with the last emission regulation. The main sensor that we used were 2 kinds of sensors. One is inside the cylinder to monitor the pressure in the in-cylinder area, and another one is an instrumented spark plug that we use to gain the data of the pressure inside the pre-chamber. And finally, exhaust gas measuring system to see what we can gain from a pre-chamber from a TGI combustion system. So the tests that we did were done with road gasoline for 4 throttle openings and 4 different regimes. The lower one are used to evaluate the most critical area of the engine in terms of emission. The 9001 is the peak torque, and the 10,500 was the peak power regime of the engine. And obviously, the pressure traces are gained by this sensor and to be used to validate the model that we built with OpenFlow. These are the strategy of the test that we follow. So first of all, we found the MBT spark advance of the engine that is called standard here. That was corresponding to an MFB50 of 8-degree crank angle, and then we tried to retard the spark advance and see what kind of behavior had the engine had. And then we came to the standard spark advance, a back-to-back test, and finally we went with the linear value of lambda and trying to every time to come back to the MBT spark advance. These are the work that we did in a strict collaboration with the Politecnico of Milano, and in terms of simulation and validation of the model with this engine. So it was a full cycle simulation was performed, and we choose peak power regime at full load. And as you see, in terms of mesh, there are grid refinement around the valves and inside the pre-chamber in order to better capture the fluid motion. So this is a focus on the flow motion inside the cylinder and inside the pre-chamber. And a really important thing that I want to highlight is that, as you can see, you have a sort of preferential motion inside the pre-chamber that it will turn in a local tumble motion inside the pre-chamber that will affect, as I will show, the combustion development. These are sorry for the anticipation. These are the validation that we achieved. That is a pretty good one. And in terms of agreement between experimental and simulation data. And the focus that I wanted to show you is that due to the tumble motion inside the pre-chamber, the development of the combustion and the jet ejection outside the pre-chamber is asymmetrical, but also thanks to due to the main tumble inside the cylinder, then after the mid part of the combustion, the tumble motion inside the cylinder is disrupting the intake side jets, and so the old jets are arriving to the walls with almost the same penetration. And so this is the second case, really interesting one, that is about a rotary engine that is fed by an heavy fuel that is used to build this drone. And so this is first of all a quick overview of the functioning of a rotary engine. So as all of you knows, you have 3 chambers inside of this engine, and in most of the cycles you can have at the same time 3 different phases. So intake, compression in the 3 different chambers, and exhaust. And this is briefly how we how the volume is spaced by the rotor inside this engine, and the formula that obviously was used to define the motion of the mesh that I will show you after. These are again briefly the characteristics of the engine and the pros and cons of this kind of application. Obviously, since the engine is very compact, you can gain high power density and a really compactness of the engine. You can use multi-fuel, and you can have a really low vibration of the engine, and most of all, also construction simplicity. And instead, the cons with respect to a reciprocating engine is the fact that it's like really high, that has really high oil consumption, and you can have high pollutant emissions. And also, since the motion will unfortunately promote a rapid wear of some parts, and you can sometimes have really low efficiency. And also the cost of the machining is quite high. So these are the rig that we used to test this engine, and a brief list of all the sensor that we used to achieve information, then to validate the model that we built with OpenFOAM. And so instead of running with normal petrol, this engine was run with kerosene to be compliant with the aviation regulation. And we tested 5 operating points at different throttle angles and about a constant engine speed. And finally, we gained pressure traces that we used in the CFD model. So this is what I mentioned before. So the mesh movement was achieved by a mesh deformation approach, and an arbitrary mesh interfaces was the model used to ensure the gas exchange between the 3 chambers and the intake and exhaust port during the simulation. And also, in this case, a full cycle was simulated. This is briefly the velocity of the fluid, the velocity path of the fluid inside the chambers. And one thing that I really want to enlighten is that sometimes at every cycle you can have a backflow from the intake side to the exhaust side when the rotor is at top position. And okay, this is one of the validation that we did of the pressure curve that we gained from the test bench. As you can see, we have kind of a good agreement of the pressure trace. The only mismatch of the simulation curve is at the compression in the compression phase, and we also have a slightly different behavior of the heat release predicted by the simulation with respect to the experimental one, but we gain a good agreement with experimental data, especially with the scatter scatter curves. And this is at a full throttle, so full throttle opening. These curve instead that are only the heat release rate are a different lower throttle opening. And we saw that in this case we have a slightly poor with respect to WOT condition, a slightly poor agreement with respect in between the simulation curve and experimental curve. Finally, we try to do an optimization of the recess of the rotor in order to see if we can gain performance and if we can have less knocking onset of this kind of engine. And we saw that moving the recess to the leading edge, we can lower the fuel consumption and we can improve the performance, as you can see, with looking at the indicated power and at the indicated torque. If you can see, these are the three different flame developments of the optimization that we did, and as you can clearly see from the two graphs, the leading edge recess on the rotor can give higher heat release rate and also higher turbulent kinetic energy that can result in a faster and a better combustion, and so higher performance. So finally, coming to the conclusions, due to good numerical and to experimental results agreement, we draw some information from the validation of the model that was done through OpenFOAM, and especially coming to the TGI combustion, we had the possibility to see the flow field evolution inside the main and the three chamber, but most of all, the fact that that obviously is impossible to see it in the real life, that we had an asymmetric development of the combustion inside the pre-chamber and then also outside it due to an asymmetric jet ejections. And going to the rotary engine, thanks to the agreement of the pressure curve of different engine loads, we had the possibility to analyze the combustion developments inside a quite different shape of combustion chamber with respect to a normal reciprocating engine. And also we had the possibility of optimize the rotor recess in order to gain some performance before obviously machining it. So to coming to an end, we had to thanks a lot this strong collaboration that we had with the Politecnico of Milano, because it helped us a lot to going on with the new design process and to go on with the innovation and development that we did every day in our company. Thanks to all of you, and I'm open for question and curiosity.
So questions and comments. So maybe I can start the rotary engine. When I read the title, I was surprised, but can you elaborate a little bit why this concept in this particular case?
First of all, we had this commission from a really important company to use an engine that must be quite compact, and unfortunately, since it is used on a manned drone for military application, we cannot since we cannot use petrol to run it. We were asked to optimize and to map the engine with heavy fuel. That was the principal reason, and also the fact that it must be as compact as possible because this drone is quite little, and so it must be quite light and compact.
Okay. So and if I may ask, so the high speed, the rotation speed that you have with this type of engine, is that an advantage or disadvantage? And heat losses, which is always something to worry about with this engine, is that a topic of concern here?
Okay, the fact is that it was now we are trying to better understand, in fact, as you said, the heat losses and the heat transfer, especially on the rotor side, because up to now we didn't have a really clear idea, unfortunately, on what is happening from the point of view of heat releases. And now we are doing also with another guy, with another student that is doing his thesis in our company the measurement of the temperature of the rotor from a sensor to see, and then probably also build a model and be predictive on this. On this
Okay.
side.
Very good. More questions or comments?
Yes, please.
One, two,
Please.
three.
Rifando l'informazione che vedi come company come di strategy.
No. No, we didn't have any contact with them.
Might be something. And another thing, is for communication from different. There's also an American company that developed.
Okay. I don't have in my mind now this company, but probably I already heard something about American company doing stuff like that, but yeah, no recollect.
No.
Thanks. Please.
Yes.
First, responding to Christian's question about why rotor engine, we've been working on rotor engine quite some time now as well. But I guess if you believe that the typical long-range passenger vehicle or even heavy duty, it makes more sense to have a smaller battery attached with the range extenders. We believe this rotor engine is perfect for that due to the compactness. So for that purpose, the efficiency is really not the most critical factor for those engines because it's not going to be used all the time. Right? And then going it back to another point, which is to the speaker, is heat transfer, considering the fact that it inherently the rotor engine has a higher surface volume ratio. Heat loss and flame propagation near the wall quenching, those are very critical issue in our experience. So I would like your opinion about your experience while working on this in terms of your combustion models to capture those aspects near the wall. Okay. Have you looked into that aspect already?
If I have to be completely clear, I'm not I was not directly involved in building the simulation model. So please go ahead, Tommaso.
We work together on the simulation of
I was aware of that.
I think that so far we really try to have a first set of good validated data to have trends which are consistent with experience. What we are doing at the moment is really start looking at the flow near the boundary so that we can have a better estimation of its losses and also of the particular shape of its release rate that you can see is not going, not just decreasing, but there is in the period. And you can see that, for example, with the K omega, we can get a better result compared to the epsilon. So the interaction between flow and flame in fact is very crucial, and the improvement of the mesh, really having a good boundary layer, we also considering what Max has shown before. I think this is even more important in a rotary engine rather than a piston engine is important. So it's something that we are looking at. But if you can see another problem, let's say another issue is that many cycles are not having a regular combustion. There is some ignition at the end. So this is also another point which is important and that we are trying to incorporate at the moment.
Yeah, we share the same experience. I guess all these basic turbulence models, combustion models that was taken for granted. Many of these IC engine simulations need to be revisited.
I think, yeah, but here I think it's more like a flow flame rather than the combustion model itself is when you get a good wrinkle factor, it propagates the flame or it doesn't propagate things. More attention to the flow features, it's most important.
Well, when we are using hydrogen as a potential fuel, then you will face more difficulty near the wall because you flame so fast near the boundary layer, which is unreal because you are not expecting so much of a burning there. So those need to be revisited in the moment.
Yeah, thanks for that.
Thanks a lot.
And we have one, yeah, Bart.
On your PGI simulations.
Yes. Okay. In our application, in our case, we gained a really stable, like really good cycle-to-cycle variability, and we had no issues also, for example, in starting the engine. And also, we had the possibility to map the engine stoichiometric lambda and above one sometimes. So we had really good results in terms of efficiency of the engine. Yeah.
But normally what you like to see is that because cost combustion and thermal efficiency goes up, which heat loss quite significant. So
Yes, that's true. In fact, we had really we had to investigate heat losses a little bit more, also through CFD software. But what we've seen is that we achieved really good performance, especially peak torque regime. But nearly similar or a little bit lower performance in all the other regimes, and we suppose that is partially due to higher heat losses. Yeah.
Yeah, we experienced.
All right, Andrea.
Yes, my question always on the chamber.
Yeah.
I don't know if you have looked to each point of the diagram you are of the combustion diagram.
Yes.
So is it the hypothesis of is this hypothesis of fully premixed valid, or you are more on the reclad flame, or
Okay.
have you checked this, or
We tried to check on the Borghi diagram, and we know that the regime, for example, cannot be simulated with a normal ECFM model, because the flamelet model is not fully capable to model the little jets coming from the pre-chamber. And also, so we started to look at the thin flames models, but for this model here, we didn't yet employed this kind of thin flames model, but we relied on still flamelet model.
you are way thicker than
Yes,
the
yes. Unfortunately, yes.
flame, and there is also pocket, recirculated pocket inside the flame.
Yes, exactly. That's the thing.
Can I answer?
Yeah,
The model that's got here is on Peter's correlation that actually is a little bit wider than the flamelet oil application. So it is treatment triangle regime rather good capture, but is ancient but very nice correlation. So because we tested this approach on other pre-chamber engines, and we exactly going deeper about this aspect. Tricky. We have multiple combustion regimes during this pre-chamber ignition, and thanks to this, you are able to handle this variation of consumption. So
You compensate that the such that you are going to filter from the regime with
a correlation that is wider than strict limit only correlation.
All right.
And a comment?
Please.
Yeah, so again, Hong Yin from Caltech, forgot to mention my name. We and Aramco had a few years of this project on pre-chamber combustion engine. So there's quite a bit of effort. And here's what I've been saying after our experience. All these turbulent flame correction in this pre-chamber context is overrated, in our opinion. The way it works is that when it actually burns in a flame mode, your Borghi diagram location never reaches anything close to broken regime or thin flame sheet regime. a lot of people get a little bit misled to think, just as you mentioned, when the jet is shooting out, it's so fast and turbulence, yeah, of course, the jet induces a lot of strong turbulence. But that's not burning in the flame net regime at that time. It is just simply a hot pocket of gas is shooting out, it's hydrodynamics. So fluid mechanics will capture that. And hot pocket will just displace so much of volume of the reactants. After that, then the flame will propagate and burn the rest of the main chamber. That process is flame combustion. Once you got into that mode, you'll be hardly anywhere close to the high calories number regime. So your turbulence flame-Peters correlation works just fine. So again, I don't mean to suggest this works for every condition, every different engines, but based on our experience, that is our conclusion.
So you should never say no to a flamelet. No, that's good. All right. So that's very good discussion. This is why a workshop is a workshop. Any other questions or comments or suggestions? No, then thanks again.
Thanks.
Which is pretty good mass generation. Right. So, Max, share. Andrea.
Okay, so now we start the session on the mesh generation. That is really important. I like this topic because, you know, nice mesh means nice results. And at least, and we start with the presentation of Ryan, that will present something to automatize the boring stuff, as you see. So really looking forward to see the result. So we are from the LHC company in Austria, and the stage is yours. Thank you.
Great. Good afternoon from my side. Thank you for the nice introduction, Andrea. So today we are going to talk about automating the boring stuff. So today we actually saw a lot of nice presentations with combustion results, and which was very interesting. But I would like to go one step back. I would like to go to the pre-processing. In industry, still the problem is that how do you get to a simulation which is ready to run? So I would like to shed some light on that part of OpenFOAM today. Good. First, I will then introduce my topic. Then we will go into the case setup simulation and its standardization. Then I will go into the main content of my presentation, which is simulation setup automation, and then I will finally summarize my presentation. Into the introduction. This is an overall workflow of the OpenFOAM workflow for an engine simulation, where we, as you see here, we have the case data in which we provide all the information for the simulation, for example, surfaces, boundary conditions, valve lifts. Then this data is stretched into a Python-based automation set of scripts, and also where we have a library developed by us at LEC. This uses the functions, OpenFOAM functions, for example, snappy hex mesh or moving mesh, which generates a set of files for the OpenFOAM case, and which then runs, and then we finally get the results. And today we are going to focus on this part, which is automating the simulation up to the point where we get a working simulation. Standardization of the case setup. I think if we standardize a case setup, then it is the first step towards the automation. We follow some very simple rules, and then automatization becomes a little bit easier. what we define here, first of all, that we should have a certain case folder where we have the input data. Input data contains surfaces and all your data, for example, boundary conditions and initial conditions, valve lift curves, all these things. Then we generate a set of meshes. These meshes are then contained in the meshes folder, and then when the simulations are run, they are stored in the simulation folder. How we want to standardize this further is that we would like to have a set of YAML files. So these are the configuration file, and the names of the files are very logical in a way. For example, the run.yaml file has all the information about the coro number or the start time, end time of the simulation, and all those information. Secondly, for example, numerics, similar, all the numerical settings are stored there. And then meshing and all these files. We also have some optional files, for example, which are in square brackets here. If we want to also include the spray, or if we want to actually simulate a combustion simulation. So these are the configuration files. One example of configuration file I'm showing here is the meshing configuration file. I think if you are also doing a lot of engine simulations here with OpenFOAM, I think it is a difficult. It's difficult to get the set of meshes which define a complete engine simulation. So with this meshing configuration file and further with automation, we can get the set of meshes that we require automatically. This meshing file contains the information about the geometry, about the engine geometry, refinements, where you want to put the refinements, how much refinement you want, which surface, and all those informations, and the remeshing times that I was talking about. The engine is then split in this configuration file in a very logical way, as we always imagine it, the cylinder part, the intake ports, and in case you have a pre-chamber. So we have in a way this parts in the configuration. This part can contain some subparts also. For example, here you see cylinder is a part, and then you have cylinder head, spark plug, piston has different parts, and these parts can be consisted of one or more than one surface. So, for example, you see here piston has bowl and crown here. Yeah. Piston. Then now, each of these surfaces, as I said, they have a single STL in it, and they have a unique name. And optionally, we also provide the meshing settings here. So the meshing settings can be considered of two different parts. One is level based. So at any surface, what level of refinement you would like to put, and distance-based refinement level. So if you put this refinement, then in a proximity of whatever distance you put, you have finer cells there. And we can further, we developed it further, and then these refinements can be put as constant. So a constant number, for example, you see here on at head, we put level 2 refinement, or based on the time type. So based on the intake valve lift here, until the valve lift is less than 1 millimeters, we have 4-level refinement, and otherwise a level refinement, 3-level refinement. Similarly, we can do this for the distance-based refinement. And here we have, for example, until the valve lift, intake valve lift is 2 millimeter, then in proximity of 1 millimeter, we have 4-level refinement, and in proximity of 2 millimeters, we have 3 millimeters refinement on the intake valve seat. This proximity can also be then based on a variable, which in which case we have this intake valve lift, 85% of the intake valve lift here. We can also specify that. So it just gives us a lot of freedom in setting up the meshes for the simulations. Then I will go to the next part, which is the automatization of the simulation setup itself. I broadly divided these into three parts. First is what we want to is automatize the mesh. Then what we want is to automatize all the solver settings, which because we have user gives the input that you want to use this turbulence model, and then you still have to set up an open form case. So the automation tool takes care of it and prepares the open form case setup for you. So today I'm going to focus more on meshing and automation part because the rest of it is still under development. So starting with the meshing automation. So first I will go into surface recognition. You get an STL file, and in STL file you have different boundaries for the engines, and for automation, it is necessary that you have the names of these boundaries in a particular way. So you have to follow a nomenclature. For example, in this case, if I give an example of exhaust valve, so it's EV2 underscore valve seat. That means, of course, it's a valve seat, and it's from the exhaust valve 2. So in the meshing configuration file, this boundary will be set up accordingly under which part it goes, and all the information will be then set in the meshing configuration file. Further examples are here. For example, if we have liner, then of course it's a cylinder liner, and then for example keyword with PC, then the surface will be assigned to a pre-chamber. In this way, we do the surface recognition. Then the most actually important part of this is the meshing times, because we need multiple meshes. So we have multiple events in the engine. We have valve opening, closing. Somebody would like to have a finer mesh at the combustion at ignition timing. So we need then different meshes for this. And this should be then generated automatically from this script. There are a few more factors when we want to generate meshes automatically is the valve movement, because this is important. When the valve moves, the cells stretch in the valve gap region, and because of that, if you start with a mesh and you stretch the cells too much, the mesh could lose its quality. So here we automate based on the valve movement. So how much the valve relatively moves to the last time step, and how much the valve actually moves in absolute terms. Same for the piston movement, how much the piston is moving relative to the last step, and how much the piston is moving absolutely. And the third one is events. Of course, we should have a mesh at exhaust valve opening, intake valve opening, closing, or if you would like to have it ignition or injection or combustion, whatever is chosen by the user. So this I used this automation and then applied it to this engine, which is a TCC3 engine from Michigan University. This is a modified version of it because the TCC engine originally is 2-valve engine, and we modified it to 4-valve engine. Yeah, it's a 86 millimeters stroke and 800 RPM, and we chose the base grid size here as 2 millimeters. When we see here, first set of meshes that we get here is quite easy. Yeah, one at EVO, EVC, IVO, IVC, and let's say ignition timing is one. Then the next set of meshes then are generated at these time steps where we have these conditions. The condition is that absolutely the valve should never move than 30% of the maximum lift, and it should move only at max 50% based on the last valve lift. So based on that, we get more mesh instances when the valve is closing and opening, because the exhaust valve lift and the intake valve lifts are same or very similar. Then we get exactly the same number of mesh instances here. So now we have in total 33 mesh instances already. Then I would like to go. Yes. What we see here is that in what we see here is that in this region, we had these meshes based on valve movement, but we see that the piston moves from this instance to this instance a lot. So what we will have is that we will eventually end up having bad mesh quality. So we also have to introduce some mesh instances here in between these two mesh instances based on valve motion. So in the next step, all the instances required due to the piston motion are then added. And here we end up with some of the, let's say these are outliers because they are too close, so they can be just then filtered out based on conditions that we have. So finally, we end up with these meshes. These are all of the meshes, and these are all of the meshes. We have in total now 44 meshes for the complete engine simulation. Another topic here is that the mesh refinement, and the mesh refinement is, of course, the user can always choose whatever mesh refinements they want to put, for example, on a spark plug. But one that can be automatized easily is that the valve gap refinement. It is important because you do not want to end up with a lot of cells. If you open the valve and you still have a very fine cells, you start with very fine cells, then you will end up with a lot of cells. And this is what we would like to reduce the cell count as much as possible. For that, what we do is we automatize it. And then this is based on a very easy concept of user that can set is, okay, I would like to have 4 cells when the valve is at closing, when the valve is closed. And then at different valve lifts, the user can specify, let's say at 1.5 millimeter, I would like to have 8 cells. So based on that, the level of refinement will be then calculated internally and then applied in the automation. Input, these are the inputs that one would need for the mesh valve gap mesh refinement automation. And then here is the formula based on which you can calculate the refinement level. Simple formula. As I said, based on user specified conditions, we can already apply the refinement levels. In this example, I am, for example, here showing that when I need 4 cells. So here, 4 cells when the valve lift is 0.4, and 8 cells when it's 1.5, and 8 cells when it's 3. Based on this can translate into conditions. For example, here, as you can see that below 1.5 millimeters, I will have then level 4 refinement, and then from 1.5 to 3 millimeters, level 3 refinement, and then afterwards level 2 refinement. Yeah, so in this way we can automatize, and it can be applied to different engines also. If you have, of course, a large engine with huge valve lifts, a 2-stroke marine engine application, so this can be applied to that also. One user just has to make an array of number of cells and number of and the valve lift at which they would like to have the different mesh refinement in the valve gap region. So both of these techniques, this valve gap mesh refinement and the meshing instances automatization, they were then applied. And here I'm showing few statistics about it. We had in total 44 mesh instances. The mesh quality, I think generally accepted is not orthogonality around 80, but in this case we had mostly 70. In just 3 instances we had more than 70. In this case, so what we achieved with this is determining mesh times. So now, of course, because I did that personally, and when I was finding every mesh instance manually, it takes time. It can take a day. I mean, for a new engine, if you just give a new engine and try to find all these mesh instances, it can take a lot of time. So in this case now, you don't need to spend time on it, and then just the meshing computation time is there. I have a video with me, so I can just maybe press the play button, and then you can see how the mesh look like. Yeah, so you can see how the refinements in the valve gap region are also changing over time, without keeping the very fine cells at higher valve lifts, with which you can end up with a lot of cells. So with this, then I would like to now summarize my presentation. What we saw is that I showed now today an automation strategy for specific to the engine simulations in OpenFOAM. The aim is here very simple too, because for industry you never have so much time to set up an OpenFOAM simulation, of course, and for a new user it can be a lot of effort. So to make it easier so that it's more accessible to different users in industry. This meshing automation, this was applied then to this modified TCC3 engine. And with this, we could achieve good quality meshes and with the minimum input required from the user. Our next step is, of course, now to finalize and just to polish a few bits and pieces here in the meshing automation, and then to deliver a full automation tool through which just with minimum user input, one can then generate a full OpenFOAM engine case setup. So this is what we strive for in our next step. With this, thank you so much for your attention, and now I'm happy to take your questions and your comments. Thank you.
Thanks for the nice presentation. So let's open the questions. Axel?
Yes, yeah, exactly. No, that doesn't. It's just when you have everything ready, and then you just click button to generate the mesh. Yeah.
Maybe if we can,
That takes time. Yes, that takes time. Yes,
maybe
yeah.
we
Yeah.
can try to
Tools for what, sorry?
flipping basically.
Different. I mean,
Hold on.
yeah. Still, yeah. I think this thing, I don't know. I mean, this can be really hard to automatize, but for us, we start with already clean geometry, and the naming is according to the nomenclature that we specify here. So based on that, and the tools that we generally use is, yeah, generally we do a lot of pre-processing of the surfaces in Converge Studio. So yeah.
Thanks. Other question?
Thank you for the presentation. I'm small that a question. Max asked 3 hours for the message generating the block mesh, the stack-based mesh, right?
Yes.
Okay. And did you only want a single core?
No.
3 hours?
No, this is not on a single core. So you can generate them on multiple cores. So this was, I think I should have put the information. It's on 20 cores. Yeah, on 20 cores. And you can actually generate multiple instances in parallel. So it can be even faster. If you have more resources, it can be even faster.
An idea of thanks.
Other question? Maybe I have a question on this 3 hour. It was really interesting. I suspect that it's 3 hour if you are generating the intake on one session and in parallel compression on another core, or is it 3 hour all the meshes in series?
These are in series. These are in series.
So 3 hour in series all the
44 meshes.
Wow.
44 meshes. Yes.
So because I imagine that it's also possible to parallelize not only the single SnapX mesh session in parallel, but also to say, okay, I start forward on 20 CPU, I start forward backward.
Yeah.
So
You can actually do 44 meshes in parallel if you have computational resources. You can do that. And in general, I think one instance based on how much it's moving,
So we can also-
duration, it can be 5-7 minutes for one instance.
so we can also go down a lot with the time scale.
With parallelization, yes. Just to add here after the contact details in case anybody is interested. Thank you.
Okay. Thanks, sir. Now it's time for Elix and Dormi from Vatsila that will present a new tool for advanced engine analysis.
Yes.
Thanks a lot, Stay.
All right, good afternoon. And actually, it's a very nice follow-up on this work, actually, because we are pretty much having this similar issues. And this is maybe another aspect of industrializing heavily simulations using OpenFOAM, so for engines. So this is basically a small, well, most of you attended actually 2 years ago in Darmstadt, the conference, so you pretty much know what kind of developments we've been doing around mesh movers, mesh-to-mesh mapping, and these kind of things. We have explained there quite a lot the methodology we were approaching, and this basically comes into a bundle which we call now AAT. AAT is a Finnish word, sorry, for meaning idea or a concept and something like this. So that's actually very fitting in this case. Of course, it's an acronym for Advanced Analysis Tool for Engines. Get the acronym first and find the words. Here, most of the presentation and the work here has been done, well, 2 years ago, the presentation was done by Heikki Kahila, our colleague then. He moved on to better, warmer skies, so he's no longer with us, but did most of the work, and I would like to credit him for this work. And the ball has been picked up from him by a Bullet Tech girl, who is a colleague still with us, and who made most of that presentation for me. And me, I'm the title is there, the simple and manager, so I'm not doing so much simulations anymore. But been here from the start, so I should be able to explain all the story and where it goes. To the wrong side. Quick word about Vatsila, the company we come from. It's not we don't sell products for the end consumer, so obviously we don't get to hear much about us. We sell big engines, large engines. We do the engines for most of the shipping around the world. Also for power plants, the same engine can be used in a power plant. Typically, the balancing plants that are used when a grid is equipped with a lot of renewables are coming from this type of engines. And you have an example here. We do most of the cruise ships, whatever cruise ship you take in the world, you will get a Vatsila engine on board. And for an example of the power plant there. We are a very old company, older than Finland. Sorry again. So founded 190 years ago, and got pretty big amount of personnel. So yeah, a bit over 17,000 worldwide, a bit everywhere. And basically, it's a big harbor. We've got some people there doing the maintenance for whatever ships is coming at the location. So that's who we are, and of course, we sell a lot of products, but our main products has always been the four-stroke engines there. We had two-stroke engines for a little while, not anymore. But therefore we have a big R&D around those engines, and we tend to strive to try to stay on the forefront on that technologies for these. Quick thing about the team. Eric Landomi, that's me. We have 5 members at the moment. 2 of them are here. Sakari and Kari are here. You might have met them. Bulut, who made the presentation. And then we are going to get 3 new people in the coming months. Magoram will start in April. And then we have still 2 persons who are, well, we're still looking for 2 persons. If you don't know what to do next month, you can pop me an email. What we do there is some cold flows, obviously, because we don't just simulate the engine combustion, we actually do the whole parts of the engine. So we start with the whatever is cold flow, liquid or air, like turbocharger optimizations for air ducts, charger coolers, oil and water and fuel flows. We've got problems with cavitation, with emissions, with pressures. Reactive flows, that's basically the combustion bit. So obviously, we try to touch all what we can do. Same thing as you're doing here. We are just never enough people to do it. So that's basically our things. We do catalyst as well. We don't develop the catalyst medium, but we do assemble the catalyst. It's a big part for diesel engines. And heat flows, of course, that's basically that's the key to durability. So long lifetime for our engines. So we need to stick to that. What is AATE? It's based on OpenFOAM, and here I would like to stress that we actually have been collaborating with the CFD Direct from the beginning, or almost from the beginning, on that development, because we want that part to be part of the standard release, and we don't want to have to maintain it, basically. So that's the key point. Yeah, so 3 years have been on the work. And well, hopefully it's efficient, robust. I will show, but you can basically download OpenFOAM and do it today. What I'm showing here, you can do it today. And part of it OpenFOAM. That's really the focus we wanted to have here. What's in there? Mostly that's OpenFOAM. Basically, there is nothing. It's on the dev version. If you download the latest dev, you have all these capabilities there. Then a little bit of scripting to make it work for engines, not like the fully multi-purpose application, and a little bit of proprietary software in that bundle. That's not proprietary, actually. It's the meshes are produced from a proprietary software. So last year or 2 years ago, in the last presentation, we were showing the meshes we were producing for our engines using GridPro. And in AATE, it's basically a demo case where we demo with a real engine the functionalities that are there in OpenFOAM, and for that we supply the meshes for these high quality grids. So, and actually the next presentation is going to be exactly about that engine in detail, and you will see the grades and everything. So, but all of that basically it's in GitHub. Just brief recap, because that didn't go as smoothly as we anticipated. We started in 2021. We had planned for 6 months work, and it took 3 years. But in practice, if we count the actual development time that was spent at CFD Direct for implementing those particular features that we are showing here, and I'm going to detail them a bit, it took 6 months. It's just like 6 months, like 2 months here, 2 months there, and so on. And at the end, that was 3 years. A bit of money as well, and that's an important aspect. 2 years ago, I was making a strong point on that, and I keep insisting. That's basically the kind of investment we have put. So we have, with CFD Direct, we spend a bit of money on the maintenance plan, and I really encourage you to contribute to the ecosystem of OpenFOAM. I don't care where or who, but those developments that make it to stable releases that are maintained after release after releases, they don't come for free. So they have, in this case, what CFD Direct OpenFOAM Foundation, they have about the entry maintenance plan is at 5,000 euros. It's not that much. But other plans with other partners, whoever you prefer, but please take the effort. It's not much, and it goes a long way. These amounts here that I'm showing, full disclosure, that's what we have spent. It's comparable to a full license in some proprietary software. So we are in the same ballpark. Big thing, of course, is that doesn't scale with the number of users. You've got one user, it's the same price as 100 users. You've got one simulation, same price as 100 simulations. Depends on your computing power, of course, but now you can run in the cloud anyway. Right, what's in there? We've got some challenges, we've got solutions, and we make it public. Mesh needs Mesh Mover is a key part. It's really a struggle to get good deformation without breaking everything, not having to remesh too frequently, and so on. So, and it needs to be on the fly while it's running in parallel. All of these things needs to be kind of baked in. So here we are, Mesh Mover, multi-valve engine Mesh Mover. It's available, and that's the big chunk that Haiti has been developing. That was continued by Bullet and completed recently, and that has been published, I think, in December, something like this in dev. So that's a big development there. Non-conformal coupling. That's what replaces AMI. This conserves mass, conserves everything. It's and that has been funded by the Process Engineering Consortium. I don't want to brag about Finland here, but this is actually another funded project from Finland. The Process Engineering Consortium is led by VTT, which is a research organization of Finland. And they have their own budget, they have managed their own things, we are not part of it. But they have spent a couple of years funding that development so that it gets there now, and we can reuse it very effectively. Then we have, what is this one? Mesh-to-mesh mapping, obviously, that's what I was saying. Seamless on-the-fly transitions between computational grids. That also is, we participated on that, but we had to order it from the developers there. And that also made it recently in the development version. Anything else we need meshing strategies. I think that was just brilliantly talked about by Riot before. We have other processing tools, injection models, some other combustion models also, that all of these things we can actually work as a community and also with the developers to actually put that forward and get something that is robust over time. It's partially available. So an example, this was actually demonstrated, shown 2 years ago by Heikki. This is basically this mesh mover that we're talking about. So how can we distort the mesh evenly? So in the center part, central circle, the mesh is fixed and frozen around the cross. On the outer edges, the mesh is frozen around the square, the corner of the square. And in between the two circles, we have the deformation ongoing. When it plays. Yep. And so one thing here we have that we move the points explicitly. We have an equation to move each point according to their scale function. So it's a little bit different than the implicit solvers that have been movers that have been used otherwise. Here, how it works, you define. Also, it's meant for engines, so it has a piston in there. So we define patches like was described earlier. We define the axis of motion. At the moment, it doesn't do rotations, but it's only translations. We have the moving zone, so you define which volume is going to be moving. The frozen zones, and that's very important. I will show an example later. You can decide to freeze, for example, a certain volume above the piston shift top so that this part doesn't move, or around the pre-chamber or spark plug or near the valves. And those, or even, hey, you can even freeze something that, for example, a spray. If you have a generator spray line mesh, you can freeze it and nothing moves around there. Then, of course, what type of motion? That motion, crank connecting rod motion, has been added to the type of motions a couple of months ago in dev. And so you can really use it for that type of motion. You can define a layer thickness for some frozen layers, and then there is this cosine scaling there, which defines like how from a frozen zone to another, how the mesh deforms in between. And you can, at the moment, it's kind of imposed like this, hard-coded, I would say. But in the future, we can imagine expanding that to putting any function you like. So valves is tabulated motion. It's the same plan as what we had earlier. And here is the mesh motion in practice. So we just have the mesh motion here. We don't have anything else. So it's a 2D engine valve case. And you see the deformation that is done by the mesh. Of course, there is some distortions and so on, and we get to that now. So here are some examples where we have. So now we add the modular meshing. NCC is a coupling, non-conformal coupling, that allows us to basically start with a bunch of modules, valve, ports, cylinder head, piston, whatever, and we just assemble them together and have this NCC attached between them. So. And that gives this kind of things. That these are some of the GridPro meshes that we can share with. It gives us really an easy thing. If we have to change one geometry, like the pre-chamber or a port, whatever, it's just one module to swap, and that goes very quickly. Also, we don't have to remesh the whole engine. And then here we add the mesh mover with the standard mesh deformation on the last. But then we can start with the NCC. We have, if you look here at the circle, we have actually the vertices that are kind of sliding against each other. And that's exactly what we are using here, so that we can keep some less deformation in that area where we are interested. Mesh mapping, if we move the mesh too much, then we get this kind of formation that we want to get rid of. And basically, well, the principle is used everywhere here, so everybody knows. I don't need to skip, but basically we generate new meshes and then we have to map in between. And when we put them all together, that's what we give. So this is actually from Vishal's presentation that is coming after. He made his TCC3 engine case, so that's what you're looking at. And here we have everything. We have the NCC, we have the mesh-to-mesh mapping, and we have the mesh deformation using the mover we have here. We have sliding interfaces. We have we preserve the high quality mesh in the area of interests. We can have the events where well done, like everybody is doing it, and we have a frozen zone. So that part is not even moving around there. It's still part of that middle mesh there, but not a single cell is moving at that location. And what did I do here? It's not coming whole in one place. There is a repository. You can find it in GitHub OpenFOAM IC engines. The reason it's IC engines is because from the developer's point of view, there is no reason why this solution should be the only one. And here we impose a demo using the TCC3, but you could demonstrate it with your own benchmark engine and do with your own scripts and different approaches or whatever. So they think of something that should be a little bit more welcoming than just an add a repository. So here it is. You find there your, you download basically a demo case, which includes these TCC3 engine. We have two commercial meshes made, a coarse one and a fine one used with GridPro. And then you can also have something with SnappyX Mesh if you want to try it. It's actually should be ready now. I wrote here that it's still under development, but by the way, this was made public yesterday, so it's still just in time for the presentation. We have, of course, some function objects specific for post-processing engines. The key here is that, again, we don't want to clutter the standard OpenFOAM release with that. So, but if you want to add more or anything, then it's meant to be. And what's the schedule in the future? So this is first release, a kind of beta release. Like I don't expect it to run perfectly smoothly out of the box. It should be, but let's see. Our goal is basically to deliver a V12 stable alongside the V12 of OpenFOAM when it comes out in July. So we take maybe 1 more month to package it again with a stable release, and we hope to make an update every year. And in the meantime, we welcome you to try it and report bugs and contact us. And that's basically the last slide. What can we achieve with that beyond just the cold flow or the combustion simulation that I was showing? And here is basically one big one is that we can do more multi-region simulation. Some CHT typically is very interesting to us. As I was mentioning in the opening slides, that it's defining the reliability of our engine. So here we have an example where we take that same 2D case that you've shown earlier. We add some solid components around. We have a piston, we have a liner, we have cylinder heads and solid valves. In this case, we have the one valve that is super hot, one valve that is very cold. The piston and the liner are at some in-between temperatures, and the gas flow is circulating also in between with different. And what you can see is that it basically gets this first layer. It's quite coarse here so that you can see it. The first layer gets little by little heated up in some parts and cooled down in some others. Doesn't want. Yep, doesn't want. You will have to see to believe me on that. One last things, some development. We want to focus now that this works. We want to focus more on combustion modeling. I mean, a lot of issues have been brought up in the previous presentations. Exactly, showing the problem with hydrogen or some other modeling of pollutants. There is potential to improve load balancing, additive mesh refinements. We have layer addition removal that is missing. Normally, everything should be already in OpenFOAM for using layer addition and removal. We just need to kind of clean it up and make it ready for us to use. Anything you can come up with? I mean, this is open there. And the 2D code that I put here, is basically send you to a form, which we get, where you can send your comments basically. So if you like it, if you don't like it, you can say that. And to contact Bullet more for the technical aspects and myself for the non-technical aspects. Thank you very much.
Thanks a lot for the really nice presentation. So let's open the question. So in case I can open the Pandora box of so I would like to see some more because it's a really nice presentation. It's if you can explain us and maybe we can also trigger a bit the discussion in the audience about you say that it's possible to mesh with Snappy, is it right?
Yes.
So okay. And
no, actually the meshing part is independent.
Okay.
So you can mesh with whatever you want. You need to prepare your meshes in advance, like Rayat was explaining earlier, and then you use this.
And it's been tested this also with geometries which are more complex, like for example, vent roof engine, gasoline engine, something like this.
Well, we don't have those at Aptila, so please try and tell us.
Of course. Yeah, it was just curiosity, because maybe there is the possibility also to extend the community.
Should be, yeah. You have to break it so that we can improve it.
Yeah, of course. Have triggered some question from the audience about this topic? Yeah, Lawrence.
One question. I am Scott Lawrence. Thank you, Eric, for the nice presentation. I have two curiosities. One, have you validated this approach with the TCC results that are available on
next presentation?
Okay. And second, so about if you already validated, have you found any problems with the orientation of the mesh near the valves with a general orientation of the vortex that are exiting from the valves, or the behavior is very similar to a non-oriented mesh approach? So that across the valve.
Also in the next presentation.
Okay.
I will wait.
Don't want to spoil, Vishal has to make his show.
Okay, thanks.
Any other questions?
And about interpolation error, maybe some of the audience has some experience about that. They tested the interpolation error on the NCC between in terms of mass conservation.
That should be fully conservative. That was a
okay.
requirement at the beginning.
It's pretty conservative. Okay, that's
Yeah.
so. Okay, in case there is no other question, let's thank.
Thank you.
Going back for the part two, actually, if I understood properly, is Mr. Shrestha, right? The pronunciation. And from Aalto University, they will present us the simulation and validation of the moderate condition of an internal combustion engine using overflow. Please.
Good afternoon, everyone. Thank you, Eric, for the warm presentation. And I will be sort of a part two for the presentation. Eric went deep into the code stuff, and I will make pretty videos for you. So I'm Vishal Shrestha. I'm from Aalto University, and I will be presenting run simulations and validation of full-scale IC engines under motor conditions, so no combustion today. Here we go. So thanks to following people and organization. Without them, the whole project would have not been possible. What are the objectives? So objective is to create an IC engine model setup for motor conditions in OpenFOAM. It is so which can be used for easy benchmarking. And I will be validating this model with an optical PIV data. And I'll be using two different meshing solutions. One will be commercial, and another one would be open source. And I will be also making this setup publicly available. So selection of the engine. So what engines am I using? It's a TCC3. So why this engines is because the geometry data and the experimental data are publicly available. It is a very simple geometry, flat head and flat piston, and the boundary conditions data are also publicly available. TCC3 engine developed by University of Michigan. It's a very simple two-valve four-stroke engine. I'll be simulating under 800 RPM, and the geometry compression ratio is 10:1. So the meshing, so top figure, the meshing is from GridPro, and the bottom mesh is from SnappyHex mesh. So what are the challenges in the meshings? They are valve closures, mesh motion, and mesh-to-mesh mapping, which has been explained by Eric earlier. For the challenges and the solutions, for mesh motion, we have a mesh mover algorithm from ATE, which is publicly available. We have a complex geometry, which can be solved by mesh modularity and NCC coupling, which is also publicly available. And we have mesh deformation due to mesh movement, so which can be solved by mesh-to-mesh mapping, which is also publicly available. So starting with GridPro of TCC3, I have modeled this TCC3 engine with 3 million cells at BDC, and the base size is 0.4 millimeters. Minimum gap is defined at 0.1 millimeters. As you can see, all the meshes in the red boxes has been meshed separately and has been stitched together with NCC. Similar with SnappyHex mesh, all the meshes in the green box and the yellow box has been meshed separately. And this does not use NCC and has been meshed together with merged meshes. So this does not use NCC. So this has 3.5 million cells at bottom dead center, 1 millimeter of base size, and minimum gap of 0.45 millimeters. These are the setup that I have used in my simulations. So K omega SST, limited linear, wall functions for wall modeling and pimple, and Courant number-based time study. So this is how the mesh motion looks for TGC3 engines. As you can see, this one is a simulation, and this is for the meshing. As you can see, the mesh maps to a new mesh if mesh has deformed too much. There's case for Snappy. Snappy, if you pay attention close to valve regions, it meshes more frequently because the deformation is more. So moving on. Let's move on to the validation part. So validation has been done with PIV data, and PIV data has been publicly made available by University of Michigan. Simulation has been done from 0 to 5 cycles. However, cycle 0, 1, and 2 has been omitted from the calculations. So average of 3, 4, and 5 cycles has been taken. So the validation data that I'll be taking into account are compression ratio, pressure inside the cylinder, and the phase average velocity. And to compare the PIV data and the simulation data, I'll be using indices called relevant index and magnitude index. So relevance index compares directions of the vectors, and magnitude index compares both directions and magnitude. So magnitude index, in a way, is more stringent than relevance index. Starting with the motor pressure and compression ratio, with Snappy hex mesh, we have been able to get 9.9 across compression ratio, and for Snappy hex mesh, we have managed to get 10.0 to 1. Just to compare, the geometric compression ratio is 10 to 1. And the motor pressure, the difference between the experimental and the simulation motor pressure for Grid Pro is 0.21 bars, and it's the same for Snappy hex mesh is 0.12 bars, so which is very less. So pressure difference at top depth center. So starting with the phase average velocity. So at the here you see this is the simulation data, and here it's the same but with the PIV window. And at the bottom is the experimental data, and at the right is the relevance index, and at the bottom is the magnitude index. So I will just play a bit here more. Yeah. So this is during, now it's the exhaust stroke. Now I would like to just pause. I'd like to just pause here and show you the experimental data and the experiment data here and the simulation data here. So as you can see, the jet here is very well modeled. As you can see here in the relevance index, one which is in red is a very exact match, whereas blue is opposite match, so no match. Similarly, for magnitude index, red indicates perfect match and blue indicates no match. As you can see, the jet has been modeled really well. However, we see some discrepancies in the vortex location. The vortex formation is there. As you can see in this simulation, the vortex has been simulated, but just the location of the vortex is just misaligned. So which shows in the magnitude index, it shows no match, but the vortex, it's being simulated. And for compression, it's a very good match during compression stroke. So let's see the similar, this one is with Grid Pro, and let's see the similar with SnappyHex Mesh. So now we have exhaust cycle to start now. So as we can see the similar results, the jet has been modeled really well, but just you can see the jet has been modeled really well. It's red and it shows really good match. However, the location of the vortex is being modeled. If we compare the vortex here and here, it's been modeled well. However, it is just misaligned. So that's why we see a big blue right here. Again, for the compression stroke, it is very well. It has been modeled really well for the compression stroke. Let's look at the comparison between the two meshes. So each, for this, the average of the magnitude index has been taken for each crank angle degrees and it's been compared. As we can see, this is a magnitude index, so it's more stringent. So a value of around, let's say, 0.7 is a very good comparison. And we can see SnappyHex Mesh performs slightly less better than Grid Pro. And really the big differences are during valve openings and closings. As you can see, SnappyHex Mesh does not very well model during valve opening. It's because the mesh deformation and the quality of the body conformed mesh quality of Grid Pro. So as you can see from here, quality of the meshes is very important. To better this model or simulation, it can be modeled with different modeling. So for example, with LES or different heat transfer models, it can be compared. Let's talk about the simulation time. For Grid Pro, all the 5 cycles, so 0 to 5 cycles takes about 6 days. And for Snappy, it takes about 18 days. So the reason is the Courant number criteria. It has been set both for Courant number, both of the simulation, the Courant number is set at the same. However, the time step to solve the for Snappy is more because of the smaller cells and also the mesh quality. You can see the time stepping goes really high for Snappy Mesh. So for this reason, it takes a really long time for SnappyHex to finish the simulation. To conclude, IC engine model has been created with using commercial and open source message solutions. The model has been validated with a good, reasonable amount of accuracy with the PIV data. Due to the body conform mesh of the Grid Pro, the results from Grid Pro is much better. And for SnappyHex Mesh, we require really small cells, especially near the valves. So it takes a really long time. And also because of the mesh deformation in Snappy is much more, it is more, during valve motion, the mesh quality reduces in SnappyHex Mesh. So it requires more time. and this model will be made available for use and modified. Thank you very much.
Thanks again for the nice presentation, and let's open again the question to the audience. Don't be shy.
Did you ever thought of an alternative generator like Iris or Mesh?
No, actually, I just
No, because of not have time, or just because it was a choice.
well, actually, I did not have time. This was my master's thesis. Yes.
I think it was shown by AT. We had an evaluation of multiple machines of evaluating the quality of the machine. But at the time, there wasn't, at least I didn't know of any industrial application where open source. There's a big uncertainty of any one engine simulation. But I'm not correctly. So I wanted to take out the machining uncertainty out of the equation. We went for the mesh that appeared to the measure that appeared to give us the best quality, and indeed you went down with Wipro and Wipro as the as contact. Otherwise, we start on the machine for purposes on input. But Wipro is starting on the input, and that workflow faster. That's the criteria. Then the only criteria I had at the first best machines, and so that it doesn't work. Okay, thank you. Now, of course, we are open to play.
Period of 2 days to communicate with each other and exchange ideas. Other ideas? Please?
Just a question about the solution. Computation is 3D.
Yes.
So again, the vortex with respect to it.
Yeah.
It seems that the jet is okay, but the vortex position of vortex is.
Yes.
Do you have any?
Actually, yes, the position of the vortex is misaligned. Yeah, actually, I don't have any know any reason why it's misaligned. Can be due to the modeling errors or anything. To exactly, I said, to better understand why is it happening, we can choose to use different modeling and see if that works as well.
And the point is that it could be linked to the jet. I think the jet is correct, while the vortex is wrong. So,
yes, that needs to be further analyzed.
And both use NCC for both cases use the NCC approach for the meshes, both Snappy and.
No, Snappy does not use NCC.
Okay, so it's pure standard
Yes,
mesh approach, and the Grid Pro use the NCC with that we showed before.
Thank you for your nice presentation. I have a curiosity about Snappy. I agree that Snappy is but looking at your mesh, I'm a bit doubtful on the quality of the simulation. You said that with Snappy you need a lot of time. Simulation is a volume short 100, especially where the flow is high velocity flow, so nearby the pipe. My question is, did you extrude at least one boundary layer over the valves first? Second, if yes or not, which dimension has this sand at the boundary in that region with respect to the internal mesh?
Sorry, can you repeat the question?
If you extruded at least one boundary layer at the boundaries of the valves and if yes or not, which dimension has the set at the boundary with respect to the internal measure of the region? So I mean, is more or less has the same size, or is 1/10 of size with respect to the internal measure?
Actually, yes, there are two boundary layers, especially in the above regions. And the size, talking about the size, I believe it's about 0.5 times of the base size.
Okay, so each layer is a half of the size. So also when the valve is fully opened, that you have a coarse mesh, is half of the coarsest cell inside the because I noticed that when the valve is more or less at the maximum, the medium lift, you have a central region with other force. So it is half of that cell.
So yeah, this one is about 1 millimeter. And this one,
when the valve is open. You have the thing open. Okay, and you have at this point, so at the boundary, you have a cell which is half of the cell in the middle.
no, to the closest one.
Okay, so with respect to the cell in the middle, so in the middle of the data, how much is the boundary?
Okay, so
that's the point.
This one would be 1 millimeter, and this size, the closest here would be refinement level 4.
Okay.
So, and so compared to this refinement level 4, this should be half of
So your objective was to resolve the boundary layers. So no work function, so you resolve the boundary layers.
No, this one has one function.
Why did you want to achieve this high resolution with the work function?
Well, with the in the case of nothing hex mesh, to capture this, so when the valve is just open, so here when the valve is just open, I need to have at least 4 levels of refinement just to
So
capture
it is a matter of to capture the excellent.
Time for one more question. In case, thanks for your really nice talk. Okay, so last talk from the session is from Giovanni Giannetti from Politecnico di Milano, and he will show us the full cycle internal combustion engine methodology with flexible mesh of. Thanks, thank you, Gio.
Thank you, Andrea. Okay, so good afternoon, everyone. I will try to be quite fast because I know that there is coffee break in a moment. So as you can see from the title of my presentation, I will speak about our methodology to generate grids for CFD simulation inside the device and OpenFOAM. But first of all, I would like to thank all the people who contribute to this presentation: Gianluca Enrico, Tommaso Lucchini, Lorenzo Sforza, Federico Ramognino, and Alessandro Nodi. After a small background on the future of internal combustion engine, I will speak about our methodology to generate grid for full cycle simulation based on the multiple mesh approach, and then I will show you some methodology validation. Then I will show you also the so-called closed valve mesh generation, which is based on the dynamic layering approach, and again, the validation of this methodology, and then I will skip to the conclusion. As you already know, in this period, internal combustion engines are facing their own transition. Most of the development is made for hard to abate sectors, and a lot of effort are put into try to increase efficiency and to reduce emissions. We saw already this morning with the presentation of Lorenzo that one possibility to achieve these goals is to use hydrogen engines. Another one we will see better tomorrow with Tommaso's presentation is to use alternative fuel like methanol and ammonia. Whereas a third way could be to try to develop high efficient new engine concept. And about this last aspect, new engine concept represent a new challenge for meshing procedure because it's fundamental to have a flexible and robust approach that can be applied for very different type of engine configuration. And we, inside the device, we handle the mesh generation in two different ways. One for full cycle mesh, which is based on a multiple meshes approach, and the other one for closed valve using the dynamic layering. We saw already in the previous presentation some of these applications, but I will go, let's say, a little bit in detail about these two methodology, starting from the first one, the multiple meshes approach. As the name suggests, is based on the use of multiple meshes to cover the entire cycle simulation, is an automatic mesh generation, and each mesh is valid for a specific interval. We start from block mesh as an APX mesh inside OpenFOAM. Then the grid points are moved to accommodate the piston and valve movement until some quality or user-defined parameters are satisfied. When these parameters are no more satisfied, the deformation stops and a new mesh is generated at the specific crank angle we reach. Of course, in case of simulation, we use a mesh-to-mesh interpolation to map the field from one mesh to the other. During the last year and still in these days, a lot of effort has been made to try to make it this methodology more robust and to try to reduce as much the user input. Once the user has provided all the information here, a command inside the device and utility is capable to generate automatically the full cycle mesh. If we have a look at the current state of the methodology, the user inputs required are, of course, the STL. So we need an STL for each phase, intake, exhaust, overlap, and compression phase. We need a first block mesh dict to define the base mesh cell size. And then, of course, there's an APX mesh dict since this methodology is based on the usage of this utility in OpenFOAM. Of course, we need the classical engine geometrical data like bore stroke, rod length, and pin offset. The valve profiles, valve lift, both for exhaust and intake, together with the minimum valve lift, which is let's say, quite important parameters because it's a trade-off between simulation accuracy, the smaller the minimum valve lift, the more close to reality we get, and computational time, of course. Then some mesh quality and validity parameters. For what concerns the mesh quality, we have the maximum non-orthogonality. There is a standard one, but we can change it, of course. And then recently we added some mesh validity parameters, like the maximum imposed duration, if we want to limit the stretch of the cells, and also the maximum duration relative to the piston or valve displacement. For example, we want to stop the deformation when we reach the 20% of the piston movement because we don't want to stretch too much the cells, even if the quality is still valid. I reported here an example. In this case, of course, when we generate the mesh automatically, here is one result. In this case, we covered the engine full cycle with the 90 mesh, with a maximum mesh size below 500,000. You can see, of course, that the moment in which we achieve the maximum number of cells is during the opening and closing of the valves. Of course, this is just an example. The mesh number depends a lot on the cylinder volume variation, so the type of engine we are S22 mesh, and also on the activation and deactivation of some specific refinement. Of course, this is the results of the concatenation of the all the created mesh gives us the full cycle motion like the one I reported here. This approach has been validated during the years a lot. We tested, we see already this morning some application on different type of engine, but more than 40 geometries in the context of industrial project, PhD, master students thesis. We tested for stroke spark ignition engine with tumble motion, for stroke spark ignition and compression ignition engine with the swirl motion, but also two-stroke engine with both uniflow and cross-flow configuration for the scavenging process. We recently added also the possibility to include some floating refinement. You can see here an example. Basically, it's a refinement that follows the valve movement, try to better describe some relevant flow features and to try to improve the air-fuel mixing. Here I reported some example of mesh moving, mesh generation plus mesh moving. You can see on the left a quite, let's say, simple engine with vertical valves and a flat piston. In the center video, you can see, let's say, a more complicated engine with the inclined valves, presence of a shaped piston, and also you can see there is also the presence of crevices here and there. Whereas on the video on the right, you can see the application of the FMR, the floating mesh refinement. As I mentioned, it's not only about four-stroke engine, but also two-stroke engine. Here I reported a two-stroke naval engine. Here you can see that we use for the coupling between the intake ports and the combustion chamber the Acme coupling. Whereas on the right, it's quite a particular case. We saw already in the presentation from Marmotos this morning is the Wankel engine, which is not based on multiple mesh, but it is a single mesh with the mesh deformation. But again, the use of Acme for the coupling between intake and exhaust duct with the combustion chamber. Methodology validation of this approach. Again, we saw something with Lorenzo's presentation, also from CMP. Here reported an example on a gasoline direct injection engine in which three different operating points were investigated: a low load condition at 2000 RPM and two high load condition, one at 4000 RPM and one at 5500 RPM. All at stoichiometric condition. In this case, each simulation included, of course, the gas exchange, but also the fuel direct injection, and then we performed also some combustion. You have some information on the mesh here. You can see that the internal mesh, the base mesh size is about 1 millimeter. Some refinement on the valve seat. We reach up to 0.125 millimeter, and we applied also a refinement cone for the injection, since we have to model also the direct injection of the gasoline. Here some result. You can see on the left the low load condition. In this particular condition, it was we noticed that it was really important to have a refinement cone and to provide a large spray angle, since the condition was boiling condition for the spray, and so to have an ignitable mixture, it was really important to perform a correct estimation of the spray. Whereas on the right, there are the two high load condition, and we saw that the homogeneity was better with the 5500 RPM, thanks to the higher turbulence, and this, of course, improved the charge motion intensity and so the air fuel mixing. And that's why at the Spark Advance, we end up with a better distribution of fuel inside the combustion chamber. Then, as I mentioned, we perform also some combustion validation to check all the methodology. And you can see the results were quite good with respect to the experimental data. You can see that some improvement can be done on the low load condition, since it was the most demanding one due to the low turbulence, and so we end up with a quite stratified charge, which was quite, let's say, difficult also for the combustion simulation. Another validation on a completely, let's say, different type of engine is the validation on the two-strokes diesel low-speed marine engine. As I mentioned, we use the Acme coupling for the inlet port opening and closing with the combustion chamber. We are aware that when you use Acme and AMI, the mass conservation is not satisfied if the patches are not perfectly planar, like in this case, because it's they are of course not planar. But for be sure about our result, we always check for mass conservation. And for example, in this case, with this operating condition, we checked that the mass conservation error was below 0.1%. So we were quite happy about using this kind of methodology in this case. Then, of course, we validated our results in terms of cylinder pressure and temperature, both with the 1D results and also using some experimental data only of on cylinder pressure. We can see that for what concerns the scavenging process, a good agreement, rather good agreement with 1D was achieved, since the boundary condition, of course, were taken from 1D simulation, and a similar trend with experiment was achieved, except for a small offset. Whereas for the combustion simulation, we can see that we have end up with a rather good agreement in terms of this peak amplitude and location, with respect especially to experimental results. Again, here I will be very fast. Another validation we saw already this morning is on the Wankel engine. So again, a quite different type of engine that has been validated using also the GasBin model, and has been validated, as we already saw previously, with both the gas exchange and also with some combustion simulation, with some, we already discussed it, some improvement that needs to be done, especially for the heat transfer model. The second approach we use, again, inside the device is the dynamic layering. We use it for closed valve simulation. So when we need to perform basically only combustion simulation, it is divided into two different approaches. One for the wedge, like the one we saw Gabriela presentation for CMP, and one for fuel geometry. The wedge, of course, can be used for axisymmetric combustion chamber with a flat head, and there is the possibility to generate jet-oriented grid. For the full geometry, instead, is, let's say, mandatory when we have complex geometries, especially for the cylinder head and the piston, and so we cannot rely anymore on some axisymmetry and so on. Starting from the wedge approach, we have developed internally a Python-based tool for the mesh generation. Basically, it starts from the profile of the combustion chamber, named the profile of the piston and the head. And then it's possible to generate the grid in such a way the cells are consistent with the spray angle. In this way, it's possible basically to generate a jet or a spray-oriented grid. Then, of course, you can select the angle you want to use for the wedge.
And then also there is the possibility to apply some tangential refinement to try to keep the cell size as much as constant as possible. And then, of course, there is the piston motion by using of the technique of the dynamic layering. For what concerns the full geometry approach, we use again the block mesh and the SnappyX mesh utility from OpenFOAM, and then we apply a setup for the mesh moving process. Basically, we select a layer in which cells will be added and removed to accommodate, of course, the piston motion. Some other methodology validation of this engine. One example is the engine that Lorenzo presented this morning, in which 4 different conditions were investigated. In this case, as Lorenzo pointed out this morning, we started without using a cold flow simulation, but we start from the tumble initialization and we perform only the combustion simulation. Again, this approach was validated, set up thanks also to the GASD model to get the 1D boundary condition. Here I reported briefly what we saw this morning. Basically, we started the initialization of the flow motion inside the combustion chamber, not from a cold flow, but from this tumble initialization. And we set up the lambda to be homogeneous, and then we performed the combustion simulation that we saw, in which the results were, let's say, quite good in terms of pressure development and also apparent heat release rate. Finally, I reported this example on the 3-piston engine because I think it summarizes pretty well the methodology, the possibility to be as flexible as possible. In fact, to mesh this particular engine is a 3-piston engine with opposite piston. You can see that piston top and in the bottom. We adopted 3, let's say, different methodology. We used the dynamic layering because if you see here in this moment here, when the pistons are closed, we use the dynamic layering approach to remove the cells and to add the cells, of course, when it is moving. Then we use also mesh deformation, because when the pistons approaches the inlet and exhaust port, we stop the adding of the layer and we start the deformation of the mesh. Like here, you can see that there is no more adding of cells, but just deformation both of the region. And then, of course, we use again the Acme coupling to couple the combustion chamber with the intake and the exhaust duct. Using, let's say, this technique, it was possible to keep the maximum number of cells of this engine you can see here. So with also all the intake and exhaust below 550,000 cells. We started a validation also on this type of engine. At this stage, only gas exchange simulation were performed, and 2 important parameters for this type of engine were extracted, that are the charging efficiency and cylinder gas purity, and they were, let's say, in line with this type of engine. And then, of course, the next step is to perform some combustion simulation on this type of engine. So to conclude, OpenFOAM and LibICE are a consolidated and validated tool for the simulation of internal combustion engine. Of course, the methodology is not perfect. Some improvements are still needed, but the research to try to improve the methodology is still going on. I think the 2 most important aspects of this methodology are that there is no need for external user license for the generation of the mesh. And also, you can see that it's quite general and very flexible approach that can be applied for very different engine. For example, we saw a very small Wankel engine, the 3-piston, up to the light-duty engine fueled with hydrogen, and also the large bore marine diesel engine, where, let's say, mesh it all with the same methodology. Well, thank you. Thank you for your attention, and if you have any question, I'm very happy to answer.
Thanks, Giovanni. Before coffee, question time.
Presentation related to the piston engine. I saw you included intake and exhaust volume.
Yeah.
But you said that you can stay on under maximum cell of 500,000 cells.
Yeah.
Quite impressive, honestly. And you included all these two volumes because of of the simulation, or because of?
Because it was a first, let's say, first simulation this type of engine, and so we prefer to keep also all the volume to see if there were some pressure waste, something that we were able to capture correctly. And yeah, about the number of cells, keep in mind that the mean cell inside the volume it's quite big. Of course, it's not very detailed, but in that particular region, there was no need to use a specific refinement because, of course, we are just interested on the possibility of some pressure waves. Thank you very much. Thank you.
Another question?
Just a question that could be referred to a lot of the users that are doing simulations in the environment. And I'm curious about when you have a variation of technical geometry and also in the mesh. And every time you have different theme, are you able to give to the superficial movement velocity, say boundary condition, which is derived from the kinematics of the system? So the correct movement of the piston, not just a stationary mesh, or Addison type.
I'm not sure I get the question. You mean?
Are you able to assign velocity boundary condition to the moving through?
I mean, yeah, I mean, the valves and the piston are all moved according to the, let's say, on the motion provided by the engine. So when you provide the engine information like con, rod length, bore and stroke, automatically we get the engine motion, and we apply this information to the boundary to be moved, of course, accordingly to this motion. In the mesh, of course, it doesn't rely also on the RPM because it's independent from time. It depends only on the crank angle. But then, of course, when you move to a simulation, depending on also on the RPM you provide, you have some information on the velocity of the piston, for example, and of course also on the valves.
It's a boundary condition well specified, not like the variation in the geometry and sort of succession of stationary boundary, but the speed of the walls is well in
there is a specific boundary condition in our formula. So if the wall move, the gas move with the wall.
Yes,
automatically.
Yeah. No, okay, that was the question. Thank you.
Other question? Okay, maybe I have one question, so I can then I would trigger the discussion for the coffee. If you would have one desire to solve one problem, because you said you had in the last slide, they said that there's still a progress, work in progress, problem to be solved. If you would have just one desire to a genius to solve one problem, which would you like to solve?
I don't know. I have to think. I mean, there is this approach. Maybe I don't know. Okay, I think the most probably the most required also for industry is just to try to give the less information as possible to the utility in such a way you say, okay, this is the engine, this is the STL, they do the mesh, of course.